Yes, thank you. What I'm really be talking about is an area of research that I don't think we've gone very far with in the community. And neotectonics is the a pursuit of trying to measure seafloor or deformation on the landscape that happens in the Holocene. And the Holocene aspect of it becomes important to get into the type of hazard assessments that affect earthquake insurance and building codes. And I'd like to acknowledge my co-authors here. Now, in terms of neotectonic studies of transform margins, this has been a huge area of research along the San Andreas fault system. And clearly there are many advantages for studying these systems on land, because in terrestrial systems, clearly you can get easy access to the landscape. But there are a number of problems with studying neotectonics on land, and that you've got vegetation, which covers things up, there's active erosion, and there are whole issues of urbanization that basically has screwed up the landscape before we come around to study it. On the other hand, in the submarine example, deformation is still exposed on the seafloor. It's experiencing deposition, which allows you to date things, and there is nominal human disturbance yet on most of the seafloor. And in some places, we can study the movements on land along a plate margin because it is exposed on land. On other places, we simply can't get into the neotectonics without going into the marine realm, because in the case of the Gulf of California, for example, 100% of the plate motion is taking place offshore. Now, what I'm going to do in this talk is just give 3 examples of our efforts to look at this problem. First, an example of the deformation in the floor of the Gulf of California. I'm then going to spend most of this talk talking about areas off Southern California, and then skip up to off Monterey. Now, we've been trying to just to develop the really basic skills that are taken for granted on land, but doing this in the marine realm. And we've been doing the marine equivalent of LiDAR using an autonomous underwater vehicle that we've developed at Mbari. It carries a multi-beam sonar on it, and it gives very high-resolution seafloor maps. It also provides chirp data, so you can look at the immediate subsurface structure. And we also operate in ROV. It's equipped with a vibrocoring system on it, and I would basically maintain we can use this vehicle very much the way geologists on land have done their field work traditionally. Before going into the data, I'd like to point out that there's a whole issue of bathymetric resolution, and in many regards, surface ships can collect some wonderful appearing multi-beam data, but the reality is the resolution that's actually being collected on most continental margins is you're lucky if you get a 25-meter pixel size with about a couple meters of vertical resolutions, and in most regards, this is completely inadequate to study near seafloor deformation. But with an AUV, which is flown down near the bottom, carrying this closer to the source, we can now routinely collect bathymetry that has a pixel size of 1 meter with a vertical resolution of 10 centimeters, and this is getting into the realm of flown LiDAR surveys on land. And I'm going to show you a series of images here. We're zooming in on the Gulf of California. These are 3 surveys that we've conducted, each about 6 square kilometers, and we're just going to fly down along the transform fault. And here's the fault going along here, running. It's a beautifully clean line. Here's a feature on the seafloor again, and we can see the fault going on, and then the sort of the details of it as it runs up to the north. Another section running here, it's just this groove on the seafloor, it runs along, and it's a line ripping on the seafloor. And I'd maintain at that level of resolution, you can go down to the seafloor and find exactly where the fault is crossing the seafloor, not sort of kind of, but within, in many cases, a meter of 2. Now, I've just been talking about surveys we've done in the Gulf of California. In this case, there's something on the order of 8 centimeters of deformation that's going along in that fault system. It's probably not surprising that those faults are vividly obvious. I'm now going to move up to Southern California, where again something like 20% of the plate motion is offshore. Now, in the case of Southern California, there are active fault maps that go on, and onshore, these maps have been really carefully scrutinized. Partly scrutinized to make sure that when they say an active fault map, it's actually a fault which happened in the Holocene and the like. But offshore, our understanding of the tectonics is largely grandfathered in. There's an admixture of paleotectonic features in there. Knowing that they're young is something which has really been impossible to do. And sort of as a result of that, the offshore hazards are really poorly understood. And I would maintain that's because we've had a lack of appropriate technologies previously. So I'm going to go and give you another cruise along a series of surveys we've done. Each one of these, again, is about 6 square kilometers superimposed in the bathymetry. That's a right lateral offset. That's pretty clear where the fault goes through there. You can actually see it in the chirp data. You come up here, there's a nice little right lateral offset. It's not as clear going across the seafloor in this area where it goes. Not all surveys work out well. Here is a ridge which is split across, and its level of detail, you can basically, there's no question where the fault goes, and even within the larger groove, you can see the places where it goes. Here it cuts this channel, sides, flank off, the right lateral offset, it runs up along the seafloor, runs across the seafloor. Here's another example, the fault goes along, and there's a right lateral offset in this, on the wall of this channel too. And I maintain that we can locate where the fault crosses these features in many cases within just a few meters on the seafloor. I'm now going to jump over and show you one more of these video zooms of the seafloor. This is the Palos Verdes fault. In this case, the fault's believed to run in here. It runs up. There are offset features that we see here which provide piercing points in here. There's a slide scar wall here, which is apparently is a piercing point for this. And then we can see a structure running across the seafloor here and running up here along the seafloor. Now, I think that based on the seafloor morphology, this is pretty clearly the most recent event. It turns out that the mapping historically has put it over here where there's a larger feature which shows up with the surface ship data quality. Now, I'd maintain in the case of the Palos Verdes fault, this is one which has obvious societal interest, and because this fault runs into Long Beach Harbor. Long Beach Harbor is the U.S.'s largest port on the West Coast, so it's got some clear societal significance. Now, what I'm showing you on the right here is one little clip of the data. This is a feature on the seafloor that's highlighted here. It looks very bold and beautiful in that multi-beam data, but I'd point out that that feature there is a 25 centimeter high scarp. No, so it runs across the seafloor, and in the case that we use the chirp data, we actually know that it's a fault because when we cross that feature, there's a displacement in the subsurface. If you go up and look at this on the seafloor using an ROV, you can go down and actually, using the sonar on the vehicle, you can locate this 25 centimeter scarp, which only shows up here as a subtle shadow in the data that's associated with this feature. The importance of that is that you then can go down to the seafloor with the ROV outfitted for coring, and you can collect cores at whatever spacing you want. In this case, we collected cores at a 20 meter spacing, and I'd maintain that this is the marine equivalent of trenching on land. And we've done that in this case and collected this transect of cores corresponding with this chirp profile. The thing I'd like to point out is, in this case, in this transect of cores going across this one little depression, which is pretty clearly associated with the fault, we find one event layer in these cores and the like. You can date the material above and below it in very traditional stratigraphic ways, and you determine more than the important thing, that this is a Holocene active event. This structure deserves to be on the active fault map. Now, to actually get at the number which becomes almost most important for seismic hazard assessments, you want to know what the slip rate is. And you can do this by the offsets of features, and frankly the next talk, which by Danny Brothers, is going to be using the piercing points in this survey to calculate a slip rate. I'm now going to jump up to off Monterey Bay, and talk about the San Gregorio Fault. The San Gregorio Fault itself is a Holocene active fault. It's well known where it crosses the land in a few places. There's been clear stratigraphy that says in that area it's Holocene active. It can be traced from land along the shelf, and it gets fuzzier, its position gets fuzzier as you actually get near Monterey Bay. But it is one of the best known offshore faults, and it is mapped across the flanks of Monterey Canyon. And we set out to study this because it's a seemingly ideal site for a neotectonic survey using the techniques that we've got. And we've had no problem finding faults elsewhere. So here's just the surveys that we've done, and this is one flank of Monterey Canyon, and the existing maps have 3 strands of this fault running as beautiful lines across the canyon floor. Now, in all fairness to those lines, they were drawn at quite some time ago, based almost entirely on the low-quality bathymetry that existed at the time, but they've persisted in the database. Now, when we went out and did these surveys, we did not identify any fault-related bathymetries on the canyon flanks, certainly not where the fault's mapped to be. And in the CHIRP data, we did not identify any through-going faults in these profiles either, corresponding with these features. But we did identify one fault that's 1.5 kilometers long. It's on the side of this slump scar on the canyon floor. It has an offset in it, and we went and sampled the strata on the side of this slide of face to try to get at the stratigraphy of the reflectors, which are offset by this fault, to get the chronology. And this is a simple game of doing field work with an ROV. You can just go up anything which outcrops. You can use a push core into the walls of this slide scar. This case they're pushing in. You can get pieces of material, and of course this is marine material, so it will contain forams, and the forams become datable with stratigraphy, which allows you to get this material quite easily. Now, in this case, we found in the samples that we have measured so far that the walls of this slide scar are clearly Pleistocene in age, it doesn't look like this is a Holocene active fault, although I as yet haven't gotten the C14 data back from the top. I'd like to point out that this particular feature is the subject of a poster this afternoon. One more comment, there's another poster which is going on right now, I suggest if you're interested you look at it. It's been given by Dave Cruz, where I've been talking about AUV bathymetry, where we are making use of the 1 meter resolution data. Dave is actually going to be presenting some of the work which has been going on at Embarra to get at the next level of resolution. And he's going to be showing 1 centimeter repeat mapping topographic surveys. These obviously have great potential for hazards assessment on the seafloor to capture things as they move. And sort of finally, I think the seafloor mapping resolutions are really catching up with the flown LiDAR surveys on land. Surgical sampling of the seafloor is possible, and I think the technology is enhancing the neotectonic capabilities, and I pointed out these posters. And I don't know if there's going to be any time for questions, but I will just play this movie again if there is.